Quality control is a branch of statistics that uses an application of statistical techniques to measure and analyze the quality of a product, service, or process. The statistical foundation of quality control includes descriptive statistics, population and sample, probability distributions, and control charts, among others. Primarily, descriptive statistics help us summarize the characteristics of data, including measures of central tendency and variability, mean, median, standard deviation, etc. In essence, it aids in our understanding of a process or product being measured, which is necessary for quality control. Moreover, in quality control, the population refers to the entire set of items or processes being assessed, while a sample is a subset of the population that is considered. In this case, statistics is used on sample data to make inferences about the population. Additionally, we have learned in this course that probability distributions are essential for numerous reasons. The same is true for quality control. They are used to model the variability in data. Many quality control methods assume that the data being considered mirrors a specific distribution, allowing for the calculation of probabilities and control limits. Equally as important, control charts are powerful tools in quality control used mainly for monitoring and detecting variations or defects in a process over time. They offer a visual representation of process data accompanied by control limits derived from statistical analysis and help distinguish whether or not a process has unusual patterns indicating issues. Quality control plays a vital role in the world of engineering by ensuring that products, manufacturing, and services meet the required specifications. Quality control helps solve a multitude of problems. As an engineer, you want two things for your product: for it to be optimized and consistent. This can come in a variety of ways. In an assembly line process, for example, statistics could be used to continuously evaluate and refine the process. By detecting defects, testing performance, and investigating these problems, engineers enhance efficiency, reduce waste, improve the product, and ensure safe, reliable products. As an engineer, specifically one in the field of quality, you want all parts and products to be made correctly the first time around. An incorrect part assembly or manufacture can create a butterfly effect of problems down the production line. Being able to use statistics to infer how likely a product is to fail is very important. Mistakes, especially engineering ones, can be very costly, which is why it is very important to always have an attention to detail. Knowing how to implement statistics into the workplace is a very important skill that can help the team analyze information and move towards fixing whatever might be causing problems. However, not all of the parts are made correctly sometimes. This is where root cause and analysis comes into play. RCA is defined as a collective term that describes a wide range of approaches, tools, and techniques used to uncover causes of problems. This aspect of quality is explained in the name, where the engineer researches all of the steps made in the engineering process to determine the root cause of the problems when failures or defects occur. Failure analysis, statistical analysis, and quality audits are just a few examples of root cause analysis. Another quality control practice that is important for maintaining the condition of a product/system is the use of continuous improvement. In the world of engineering, practices are constantly improving in order to meet the demands of the consumer, while also churning out the product as quickly, efficiently, and safely as possible. By collecting and analyzing data related to product quality, customer feedback, or manufacturing metrics, engineers can identify opportunities for enhancement. This iterative approach enables them to make incremental improvements and optimize the overall quality of their products or system. Control charts are used in order to monitor quality. It is essentially another way to present data. It attempts to present a certain variable on an engineer's part into a normal distribution. There are three lines in a control chart. The center line, typically the design specification for the variable, then a lower and upper control limit, also known as NIST. These are typically defined by a 3 sigma deviation from the mean. However, this designation is completely arbitrary. The upper or lower tolerance for a variable might be less than 3 sigma. For example, for a part that must be manufactured very precisely, there is no point in following this 3 sigma deviation if the variable needs to be under a 1 sigma deviation. The bounds for the upper and lower control line is determined by the requirements of the variable in question. Once these parameters are set, any data point that exceeds the control lines in either direction is labeled as out of control. This is deemed a type 1 error, and further investigation will be done as to why the variable was produced incorrectly. A process that consistently produces within the control limits is deemed as in control. Control charts also take into account time, meaning an engineer could also determine patterns to further assess if there is an issue with manufacturing. Here are some benefits of quality control. Monitoring performance and variation. Control charts allow you to track the performance and variation of a process or variable over time. This helps you understand the stability and predictability of the process. Detection of changes and trends. Control charts can detect any changes or trends in the data that may impact quality. This early identification allows for timely intervention and corrective actions. Number 3. Differentiation between common and special causes. Control charts help distinguish between common causes of variation, which are inherent to the process, and special causes, which are sporadic and indicate a deviation from normal operations. This differentiation is crucial for effective problem solving. Evaluation of improvement actions. By using control charts, you can evaluate the effectiveness of improvement actions taken to enhance the quality of the process or variable. This feedback helps in refining and optimizing the improvement strategies. Communication and documentation. Control charts serve as a visual representation of the quality status and history of a process or variable. They provide a standardized and easily understandable format for communicating quality-related information to stakeholders. They also facilitate the documentation of quality-related data and insights. There are also, however, some drawbacks to quality control. Data requirements. Constructing and maintaining control charts necessitates a sufficient amount of reliable and accurate data. Inadequate or flawed data can lead to misleading interpretations and ineffective control. Understanding the process. A clear understanding of the process or variable and the factors that influence its variation and quality is essential for selecting the appropriate control chart, parameters, and rules. Without proper knowledge, the effectiveness of control charts can be compromised. Review and update of control limits. Control limits, which define the acceptable range of variation, should be regularly reviewed and updated to reflect changes in the process or variable. Neglecting to update control limits can result in incorrect interpretations and ineffective control. Commitment and collaboration. Successful implementation of control charts requires commitment and collaboration from individuals involved in the process or variable. This includes data collection, analysis, and taking appropriate actions based on the insights derived from the control charts. Additionally, adherence to quality standards and goals is crucial. By considering these benefits and drawbacks, organizations can make informed decisions about implementing control charts for quality control in data presentations. The implementation of quality control statistical techniques allows for the improvement of an engineer's product development, resulting in an increase of client satisfaction. With the data collected from quality control, we obtain a greater understanding of our audiences regarding safety and convenience. Such tests and feedback give us an opportunity to analyze product durability and explore areas for improvement. Staying within goals of production helps reduce time, costs, and materials, and facilitates an efficient process. Through quality control, we can document, organize, and work with others to encourage new paths towards optimization.